Hello, welcome everybody for the Learning Lab 19. My name is Marcelo Guarido, and today we're going to be talking about shallow and deep learning using neural networks from the scratch with Python. And Ryan is going to be our guest presenter. So I'm just going to start in sharing my screen. So I'm going to start with a short presentation for today. Oops, sorry. Okay, so today, like we said in the beginning, we have the title of this webinar is Neural Networks, Shallow Deep Learning from Scratch in Python with Geoscience examples. We have a guest presenter today. His name is Ryan Mardani. Ryan, would like to present yourself, to introduce yourself?
Hi. I'm Ryan. I have about 12 years and more than 12 years experience in oil and gas as a geoscientist. It ranges from the Middle East, Africa, and some in Canada. In 2016, I came here and started my another degree as a Master of Geophysics and studied here. And then I fell interested with machine learning. And after that, I've tried to, to work in a geoscience in a collaboration with data science and to get solved the problem through the machine learning and especially neural networks. And that's me.
Okay. Thank you, Ryan. So we have our hosts for this event. So we usually have three hosts. Me, I'm Marcelo Guarido. I'm a data scientist with a PhD in geophysics, and I'm the head of the Cruz Data Science Initiative. We also usually have the co-hosts as Daniel Trad and David Emery. Unfortunately, they couldn't come today, but Daniel Trad is an associate professor and chairing in exploration of geophysics at the University of Calgary. Oh, Daniel is there. So I'm going to ask him to introduce himself. Daniel, just came in time to introduce yourself.
Okay, sorry I'm late. I had trouble to connect. So my name is Daniel Tratt, and I am a professor at the university in the Department of Geoscience, helping Marcelo with the Data Science Initiative.
Okay, thank you, Daniel. And we also have David Emery that usually is our co-host, but he couldn't come today. And he's a geophysical specialist and actually is starting his PhD in Cruz, working with data science projects. So I'm just going to start with a small introduction about the Cruz Data Science Initiative. It's a subgroup in the Cruz Consortium that it's located at the University of Calgary. In this consortium, we usually work with seismic projects, but with the Data Science Initiative, we are expanding to work with any kind of data in geoscience and engineering, mostly related to the energy industry. And they are both focused for academic and industry projects. Oh, sorry about that. We also offer some programming training. If you're interested to learn more about programming, we offer programming training in R, Python, and MATLAB. And also how to do some applications in machine learning and actually how to create applications like using Shiny and some type of libraries. We also offer those learning labs. Those are bi-weekly webinars. Those are free and open to everybody. And if you want to learn more about all the learning labs, you can visit our webpage in cruz.org, our YouTube channel, our Meetup webpage. So I'm just going to click here in cruz.org. So that's our webpage. If you wanted to learn more about our previous events in those learning labs, you can come to the research tab and data science. So we have these webinars by year, and all the previous webinars they are recorded and you can watch. Actually, if you click here, it's just going to link you to our YouTube channel. You can watch all the videos. You can see also all the videos in our YouTube channel. And as well, to stay tuned when the next events are coming in our Meetup webpage. So you can register to our Meetup, and we're announcing all our events in here. Okay, so now I'm gonna pass the voice to our guest presenter. So Ryan, the room is yours.
Okay, that's good. Marcelo, my screen is shared, yeah? Okay. Okay, today I'm going to talk about neural networks, shallow and deep learning from scratch in Python with a Geoscience example. Actually, the motivation behind this presentation for me comes from the, when I started to code about the neural networks, I used, like the others, the Tensorflow, and then changed to PyTorch, and almost 12 lines of code. This is the one example that I did about 3 years ago, but it was a little bit vague to me, understanding there's some functions, although it is very short and dense, very good, but I wanted something to understand what's the mechanic or the functions behind this. That's why I came to this presentation and this work. I want to do from scratch, step by step, and to see what's going behind the scene actually. Yeah, then after this
Ryan,
sorry.
Just a second. Are you sharing your screen? Because I cannot see.
Yeah, I'm sharing my screen.
Can you try again?
Let me try again. Sorry.
Oh, yes, now I can see. Thank you.
Okay. Okay, sorry for this.
No, no worries.
Okay. And the agenda for this presentation will be like this. We will have first some introduction and some, the basic concept about the prior knowledge database that I use for this presentation, and some introduction to artificial neural networks, computation graphs, and logistic regression as a cost function. Then we'll go for shallow learning. We will talk about these 5 steps: parameter initialization, forward propagation, compute cast, and then backward propagation and update parameters. Deep learning is very similar to shallow learning, except that it's going to have more hidden layers. And then, and finally, we will show about our prediction and visualization. Actually, to be compatible with this work, actually, it is very good to have some basic knowledge, not too deep, but a little bit basic knowledge about the linear algebra, about the matrix multiplication, adding together, or something like that. Regarding chain rules and derivation is very helpful to understand because it's totally basic, and Python 3 and some knowledge of array manipulation using the Numpy is very helpful. Some terminology is also can help us to know. I'm not gonna, define what is the hidden layer, what's the input. Just very, they are very basic and fundamentals. It's gonna help you if you go. In this problem, actually in this work, I use dataset from the Force 2020 computation data, but it is almost not too big, but almost noticeable data size. 100 wells is original, but I made it clean, came to just 3 wells training data and add 1 for testing. I kept it. And this is the data frame that you can see here. And I cleaned all the data, I left 3 predictor or 3 well logs. You see that gamma ray here. We have nitron and also density. I kept just 3, and although the lithology for this task was about 12 lithology prediction, I made it binary: shale or sand. Sand is red and shale is green. I wanted everything very simple, very easy to handle, because we are going to work on a lot of functions, and I don't want to start headache with data. I want to go with basics and fundamentals. Artificial neural networks, actually, neural networks is a mimic of human brain, as everybody knows today, maybe. It receives some information or stimulation from outside. We call it as predictors or features like X1, X2. And then we multiply it by the weight matrices. Weight matrices can be any random number, or you can use it just by one, everything you like, not zero. And then we add it together. After the multiplication, we add some bias, then summation happens, and then we go for activation function. We left on activation function because we want to destroy its linearity if it's possible. Activation function, that's very important. If we not apply it, it's gonna be simple linear regression, and it's not gonna work. After that, we will have some output, y hat here, y hat, and we have some true data. Here is our lithology. We will check the difference between together as a loss function. In total, and we will loop this process from the first left to right. It is forward propagation. Then we will use a differentiation, and we will have a lot of derivation for the using chain rule. We will drive back to adjust weights and biases, and we call it backpropagation. Just get some touches on computation graph, and to see that how in computers, most of softwares like Tensorflow have used to solve a simple function. Let's have some example. Like we have a J function. It is the function of A, B, C, and we see that this kind of function here. And if we want to solve it through the computation graph, we should define from the simplest and inside the core of the function to get out. We will store this one in the U, then BC plus A. It's going to be in a variable V, and then finally we will have a J function. And it's exactly what happens during the computation through the computer. And I made one example here. A is 3, B is 2, 5, C is 5. And we see the result here of U is equal to BC. It's 10, 13, 26 for J. And what if we wanna, minimize the J based on other, with respect to other parameters, like here, if we wanna do based on the minimize with function J with dv, we should take the derivative, and it's gonna be 2. If we go for A, it's gonna be dj over dA. It's gonna be the chain rule. We use dj over dv over dA, and it's gonna be 2. For this presentation, actually, as we are our loss function that we will get derivative of it, it is function of weight and biases. And for the convenience, we will use the denominator for all of the coding. Okay, logistic regression actually is a very important cost function. We can, this is not cost function, it is a function that make our binary classification much more simpler and easier. And it is the function that if you look at it, it is 1 over 1 plus e over minus 0. And if we multiply to any function, it's gonna divide it, it's gonna range it between 0 and 1. For this classification problem, shale is 0, sand is 1. It must be the last layer of classification, because we will have some threshold here to see that is it sand or shale. It's gonna be different. And mainly loss function in theory, some called between, it is scored, half of scored of prediction. What we have done minus the reality of this number. But in calculation through our computer, sometimes the convergence of this is problematic and very difficult. That's why for binary classification, they use loss function, across entropy loss function, and it is not very difficult. It seems complicated, but let's look at it. It has two terms here. If y our prediction, if the real number is 1, so the first terms is gonna be 1, and to get it minimized as a 0, we should have our prediction 1, and vice versa. If it is y is equal 0, this terms is gonna be 0, the first term, and the second term to get the result 0, second term y hat also should be 0. Loss function is, we call it for convenience just for one training example. For entire training example, which we have a lot, that's why we should make summation and make average. That's, we call it mainly cost function. The same loss function, just this term is added to there. Gradient descent, okay, we have a cost function that is a function of weight and biases, how we can find the minimum of this function. Looking at this graph here, it's a 3D, it is W, weight, biases, and if you want to find the minimum value for this surface, we should do derivatives by steps, go down, we initialize where, and almost we need to drive the gradient in a minus direction actually to get the minimum value. And in the for the updating this one, we should this learning rate, it shows that how big our next step should be. This is an example, actually, I found it very interesting. Different kinds of, minimization possible algorithms. I got it from this reference, and it is from a stochastic gradient descent. If we check it and look at it, the red one, it's going in the right direction, but it is very slow. But other ones like ramp or other grad, they are very good and move very fast. That can be a very good point into our future users. Shallow learning. Let's start shallow learning. It consists of one single hidden layer. And we have here for our examples, this is the gamma ray, neutron and density, our inputs. We have one hidden layer and we have output layer. We need to consider that each node have two operations inside. One is summation of the parameters, one in the left, in the right, applying non-linearity or activation function. That is also from here, and then we go to probability to check it is between 0 and 1, which one is this? For the mathematical computation, we can see that Z1 for this one. If you want to apply for that, we need to first this linear part, weight matrix multiplied by input vector, and then plus by the bias. Then we apply one non-linearity or activation function. Then we path it from the first layer to the output layer. In that shallow example, we go from the Z to calculate the same, and finally we receive the loss function. The red arrow is if we're going from the right, it is forward propagation, and if we go from the left, I will cover the left side because it has some derivation problems a lot in the next slides. But the point and actually neural network is that keeping your matrices sizes very true and very compatible together. And the rule is that when we are going to one matrix, weight matrix, it should be started from the The one layer on right, the nodes of them, we have 1, 2, 3, 4, 5 here, 5 multiplied by input 3, and then we have the vector of the input x, we have 3, and then we will have a vector for the bias, it's gonna be 5. This matrix is okay, we can solve it. And then we go to the next one, this one, the output layer actually here, we will have a weight matrix is gonna be it's gonna be 1 over 1 by 5, 5 by 1, and we will have one output for the bias. Okay, let's start the implementation in Python. The first point I'm very I think I mentioned that in the earlier that the main framework of this functions comes from the Andrew's deep learning courses. I really like it, and that's why I try to get maximum use of this and share with you. Layer sizes, we're gonna need these dimensions. Layer, we have 2 arguments, the input vectors or matrix and vector here. And it's gonna return, it's very simple, it's gonna return the input layer size, hidden layer by just calling very simple shape of the this way. Then we need to initialize model parameters. For model parameters, we are gonna use the random for the weights. It is better not ever use the zeros, but for the biases, we can use the zeros. We keep the same with the same dimensional matrix dimensionality, and then we store all the parameters that initiated in this dictionary, W1, B1, W2, B2. And remember, we are multiplying it by 1.001. This is the for calculation speed up. And calling this matrix here, this function here, we have 3 inputs, 5 nodes in the first hidden layer, and 1 gonna be the last one. You see here that we have W1, it is 5 by 3, 5 by 1, 1 by 5, and then the B2, it's gonna be 1 by 1. Sigmoid function is very helpful for us. We can use it, we can define it very simply. It is not very complicated. We can define it as 1 over Numpy exponential of the function. We can also call the tangent sigmoid, tangent tan h function from Numpy, or we can, derive it very simply by ourselves. In the forward propagation part, now we are going to derive and calculate this one. First Z1. Let me tell you that this superscript inside the bracket is the number of our layers. Okay, for layer 1Z is gonna be this. We applied 1 tan h nonlinearity on it. Then Z2, we calculate another weight matrices that already generated, but it's gonna be the input for the second layer always comes from the first layer. It is the main important of them. And then for the y-hat or the prediction, it's gonna apply our sigmoid. You see here, we used parameters from the previous function and then applied this functionality. And this is the vectorization actually we use for the Numpy. If we don't want to use the vectorization, we should have dealing with for loops, which will be split down for our calculation. That's why here we need to also store these parameters in a cache, Z1 and A1, Z2 and A2, because later we are gonna drive and do some derivation over that. After we went to the right, we need to compute the cost, because we wanted to know how different our prediction and real data has different, the same equation, but here we have as 2 layers, 1 hidden layer and 1 output layer. The output layer's results is gonna be inside this one. First, we need to define one function, compute cost, and I wrote it here in two parts, one inside the bracket and the outside. And for the keeping dimensionality regular, we can squeeze it using the Numpy function to make. Now we calculated the cost and we know that okay, this is the difference. What we should do? We know the difference. We did this direction. Now we are going to go back direction. Let's first look at the loss function here. dA2. This is the actually dL over dA2. That's why we just use the numerator as a variable name in the code. We don't actually you can derive by yourself, or there is some manuscript outside. We can use this one. I don't want to derive all equations here because it's going to be very time consuming. Please accept from it. And we don't even need this one. That's why in our next function, we should calculate just this. dz2 is equal a2 that we cached already minus the true values. And step by step for dw2, we start with this equation, db2, and then back to here to have these values, dw2, db2, dw1, db1. They are very important parameters that we are going to have them. And if you want to apply and to initiate our function here, we need to do backward propagation. In backward propagation, the arguments is parameters from the forwards. We can remember it. And the cache, some parameters from the W and A, and the input vector matrices and the output, or no, sorry, this is the Y, it is prediction. First, we need to get a shape, call the parameters from the parameter a dictionary we already saved. We have also A1, A2 from the previous dictionary called cache. And then we should do this one exactly. It is not very difficult. It's very simply, we can calculate dz2 is equal the last value of output A2 minus our one. And then step by step, we go. The important point is that because dB is a vector, we need to make sure that we are keeping the dimensions true, not to mix up from the vertical vector to turn over to horizontal vector. That's why we should do that. And then finally, we need to return the grads as one dictionary, DW1. These are the more parameters, gradients that we need to in the next step for the update parameters. Now we have already W, and we have DW, actually here DW, and this is the DB. We need to run it and get the difference updated parameters. In the first 4 lines, we called it from previous part. From the dictionary parameters. In the second 4 lines, we call it from the grads parameters, dictionary, and then simply we call it W1 is equal W1 minus learning rate. And the learning rate, there's some point about that. We should not get it very big number because it's gonna, it's gonna fluctuate a lot. Maybe it converge very fast, but it's possible. And also we shouldn't get it very small because it's gonna take longer training and convergence. Then for this parameter, we should also get out our parameters W1, B1, B2. These are the parameters that we are updating and again keeping in returning in parameters. Okay. Let's combine all the functions that we used, that we generated in the previous section, and create one neural network model. It's gonna have, these are the arguments for, we are gonna provide for this one, input, number of nodes in a hidden layer, number of iteration, iteration means, in the previous slide, you see that for all training example, we run from the forward propagation to backward propagation and calculate the updates. It's going to be one iteration. We have from the previous layer sizes, array dimension here, we call it initialize parameters. Now we have our network. We should look over the iteration, for example, 10,000. It's going to be between 0 and I don't know, but it depends on your data. It's going to be small, big, or something like that. This is not new. This is just functions that we created already. We created, generated forward propagation. We put the same inputs. We calculate cost. And then we derive the gradients for W and B. Then parameters, it should be updated based on each iteration to get minimized and smaller error as we can. And this is simple, just we wanted to print out what's gonna go. Here, shallow learning progress. We call the parameters and call the NN model this input. I use the same that already we defined, 5 nodes in inside, number of iteration, 10,000 and print the cost. You may also notice that after just 1,000 iteration, it's stuck and it doesn't, doing very good. And cost it is not decreasing, and this is not that we are looking for from the training models. And just I wanted to make sure that the dimension of the matrices and biases is true and everything based on the. That's why let's go for another concept. Test the shallow model. Write a one function like predict. We wanted to see how accurate our prediction with the test data that we did, how it's actually for the training data, running this function shows 57%. Although, yeah, I know it is a binary classification and it is not good to have the accuracy. Accuracy maybe is the last parameter and matrices to evaluate. Maybe we should think about the recalls or precisions or other AOE, other for the classification problems type. But just for simplicity, I used it. And for this presentation, I'm not looking for the result. I'm looking for, the mechanics, how it works and how we can learn from the procedure. For the test data, actually, that we kept from the training, it showed 40% accuracy. Not good. Let's go for deep learning. Deep learning, it's different from the shallow learning, just based on the hidden layers that we can have in our network. Deep learning, by the emergence of the strong computers and calculation capability, deep learning came out, and nowadays you can have maybe more than 100 hidden layers with a lot of nodes inside. It's computationally expensive, but still our computers, home computers, can do most of them. Here we have again the same calculation we did, just I'm telling this over and over because it's very important, and neural network is nothing more than this, but this time we should keep the record of our layers. This is one layer, this is another layer, layer 2, layer 3, and layer L we have. Again, forward propagation, we have W's, calculate activation, and then we need to preserve Z1 as a cache. We need to keep out. Later, we are gonna do some operation on it. And then we go, after finishing forward, we are gonna go back and calculate the derivative of the loss function over our interest, dw and db. And then again, we are gonna apply updating to get the most and more accurate weight and biases that can help us for the minimum problem with in loss function. For this part also, I will use the same Andrews procedure for the deep learning. I'll initiate the parameters for L layer network. Then we will need to do these 4 steps one by one, each helper function. Then we will stack together like here that we see. But the point is that for binary classification, we should consider the sigmoid as the last activation. We are not allowed to use ReLU function or other functions. The best is sigmoid, because for this binary classification, we want to between 0 and 1 shale or sandstone. And then again, like the shallow, we will compute loss, backward, and update parameters. Let's go here. Keeping dimension of the matrices is very important. Let's look at the layer 1 here. Layer 1 is the number of nodes, the dimension of the W diagram nodes multiplied, and we have 3 columns here. The shape of the B, the same similarly, it is a vector, vertical vector, and the activation. There is no very important point here, just the point that I wanted to mention, that when we go into the last layer of the deep network, the last layer's weight matrices, it should be L-1, because 1 to the left of the networks. Sometimes keeping this dimensionality makes it like headache for you, and it's gonna be difficult. And the number of the features here, you see that we apply in the right side of this matrices. Okay, let's start by again in the deep learning initialize parameters for L layer. We will use very similarly, just this time the input of the argument that we should provide for this function is layer times. It is a list, Python list, and like we have here, we can also use the array. But the point is that the first and last one we should be considered very in detail, because this is the features that we are going to use, or predictors, and this is the output. And then for this example, we use 5 hidden layers in the first one, 3 in the second layer. And then we should look for over between 1 and L, which is the length of our network's layer times that we provided. And checking out the weight 1 and B1, we see that almost it is consistent. And this is the one example that I wanted to show that our matrices, our function works well. Let's start by forward propagation, but we should have 3 layer parts here and 1 in linear parts. Linear parts is very simple. We should get A, weight, and B. It is simply a dot product, or we can use a Numpy dot, and inside the bracket, inside the parentheses W and A, we should preserve the cache A and cache, and also the Z for this calculation. Then we will go for the another part from here. Maybe this is the repetition again. Activation function, we will use both of them in this work, sigmoid and ReLU. ReLU, sigmoid, we already familiar with it, and ReLU is the very, very efficient function, actually, activation function, and it is between 0 and Z. That is doing very good, actually, based on I've done a lot of tests, and it's very reliable function. doing the second part of this activation function, we need to decide, actually, we are gonna do this one, this equation. We will multiply weight matrices of layer L multiplied by A, which A comes from previous layer, for not color, for the current, not the previous one, and we add with the bytes. And then this activation function we will decide inside the linear activation function. We will call it, if we call it sigmoid, it's gonna use the sigmoid activation, or if we call it ReLU, it's gonna be ReLU function. It's totally up to us, but again, for the last layer, we should consider it must be sigmoid. Let's go for the last part of this part. We will add up two functions from the previous works and make one function that is for whole model, but the last here activation function we should call for sure it is sigmoid. We will use the previous function's parameters cache. No, this is the from the linear forward. We should the A previous functions because L minus 1, add the parameters, and it's gonna give us AL. If you can remember from the previous slides, for the shallow learning, it was A2, very similar to that one, but here we use the last parameters, that one. Okay, now again we landed and again cost function. I'm not going to talk about this, just this is the last layers A. Okay, the same function. We have now, we are here, we did loss function, we come back here, we want to calculate backpropagation. Backpropagation in deep learning a little bit challenging than the shallow learning. We should consider the dimensionality and also the W's and dB. Let's go and see what we should do here. The same, very similar to forward part, we have three steps. We should calculate first linear part, but the linear part comes from here. If we wanted to do dW layer L, we should calculate this derivation, and based on the derivation, it is 1/m dzl that we have here, and then A from the previous layer transpose. Then we go to dB for L layer, and we calculate the activation of the previous layer, because later it's gonna come for the latest input. I think, yeah, for the calling the function is not very complicated. You have a function here. We write it. We make a dot product of the dz over AP transposed, and then finally we need to return dB dW, and this is the just linear part. In the second part, we need to have we need to define the activation function for backward. There's very small difference between this sigmoid. ReLU is almost the same, just we need to keep the copy of the dz calling to forward. But sigmoid is a little bit different, and we should multiply after that. dz should be dA multiplied by s sigmoid function and 1 minus s, and we should bring it back dA as a backward sigmoid. We use again, we generate the linear activation backward. This is the second step. We call the functions, and we call it which function we want to use as activation, ReLU or sigmoid. We are free for in the middle layers for this problem. And then we call the redo backward. We use the DA and activation code from the previous part, then go to linear backward and use the DZ and DDR. We need to calculate DA from previous DW and DB. We need to again return these values because in the last layer, last combination of this function, we required it. I talked about this here. Actually, the output is here. We have sigmoid as a last one. Now we are deriving this way. Let's combine all this just for backward part. We want to do backward. We want to do linear loop. We call it L-1. This is the that we keep, and this is the for sure. This is the for the last layer that we should use sigmoid. The import, the arguments that we are gonna fit for this function A, L, Y, and caches from the previous inside, previous the function, and then we need to preserve the grads. Very important for us because everything we are doing here just calculate the gradients and keep them for as later we will update our model and update the beta and biases. Then initialize the backpropagation using this equation divided by 2. Then call it which actually sigmoid. We should use the linear activation backward. Using that one, we will have the gradients for DA, DW, and DB inside. And then we are gonna loop over the layer L length of the caches, because as you can remember, the caches comes from the previous functions, and in the previous function we defined that the structure of our model is how many layers we have. That's why we go there and then we calculate grades and keep the grades. Again, here we have updating parameters to get the W and biases based on the learning rate that we will define, and then we keep them as parameters in a cache. Let's combine for this model as a deep model. We call it L-layer model. Very, very similar to this, but for this function, we are gonna have arguments input X, Y, our target values, layer times. It is the list, Python list. We should introduce how big or how many hidden layer we wanted. But remember, for the layer times, we need to introduce for sure that we have input and output layers dimensions. Learning rate, small or big, up to you. And actually for the calculation time, iteration, and also we want to print the results. It is done nothing new here. All functions we defined, we just loop it over the iteration from 0 to a number of iteration. If, for example, we use 3000 iteration, it's going to loop 3000 this function over these functions. L model forward, we go forward, again we compute the cost, we go backward propagation, we calculate the backward, update parameters, and then show the results. Okay, for this problem, for this lithology problem, I use this model, 3 inputs. I have 20 nodes in the first layer, 20 nodes here, 10 in the second layer, hidden layer, 8, 5, and 1 the last. This time we're calling and creating to plot the cost. It seems better than, of course, shallow learning. We see that from first iteration to 1000, it was 2, and it started to to decrease. And when we plotted iteration over the cost from 2, it goes to 0.25. And it is good, actually. It is, although we have a lot of, difficulties to come here and calculate this one, but it seems understandable. Let's use the same predict function between the reality and between our computations results. And again, accuracy is not good for this kind of binary classification. We should use true positive, negative, and this kind of, recall or precision kind, but it is not accurate and 91% of the accuracy, but this is the most and the simplest deep network that we can create. A lot of hyperparameters we forgot. And for this test well, I plotted here again, we have the gamma ray, nitron density. We have 3 of them are our predictor. This is our target through lithology for this well. And this is our prediction from deep model. Shallow model actually was not good, and it doesn't even, worth to mention and plot it here. But deep model actually, it could understand the boundary between shale and sand. And very interesting that in this level we see, because the peak is very high and the signal is very high for prediction, it was successful but for the rest of the gamma rays and densities, you see data is not very, very profitable for the deep model. Okay, as a final thought, for this presentation, I wanted to show the procedure and the implementation. And it was very important for me. Then the good result, even though the final result for deep learning was much better than shallow learning. And this is the simplest one, and there is no guarantee it's gonna work for all models. We didn't cover a lot of things here, like overfitting, underfitting, or regularization. A lot of hyperparameters in a model can help. But on the other hand, this is very helpful for me to understand what's going behind the network, how I can implement this work through the Python Numpy. When I used Tensorflow, it was very good, friendly, simple, but understanding the mechanic behind caused me that I want to do it and write it function by hands, although it cannot be very good like using PyTorch or TensorFlow to make it for your own use. Okay, these are the references. Actually, I told that the main framework I used from deep learning from Andrews, and the database that I used for this kind of database for the Force 2020 and database, and I have clear data. Later you can use the data, and also Jupyter Notebook is ready. Okay, that's all. Marcelo and Daniel, I'm ready for any questions that I can answer.
Thanks a lot, Ryan. That was an amazing presentation. Now we're gonna open the room for questions. So if you wanna ask anything, you can unmute yourself and just ask. Probably I'm gonna start asking something. So you're also gonna provide the Jupyter for us. So it's your GitHub page.
Yeah, it is ready. Actually, I provided and almost neat, and you will have access to the data. You will have access to codes, almost identical with this one. You will go for all codes, and it's good to try, actually.
Okay, nice. So I have one question about your final predictions. Basically, you can go back to your presentation. I think it was slide 39.
Yeah.
So I see that your predictions are quite good when you have like a large blocks of shale and large blocks of sandstone. But those thin layers of shale, I think the model was not able to predict. Do you have an idea why?
Yes, I have an idea why. Data. You know, every magic that we do in machine learning comes from the data. If your data is clean, I mentioned that if make it larger here, if we have, you know, very big and noticeable peak that makes it different from the previous reading of your predictors, yeah, model can understand. Okay, can show that, okay, this is a little bit different. And on the other hand, maybe I should have used a lot of data. And the last point I can mention, this lithology that it mentioned, it is some interpretation from the well logs provided by the data set. Maybe it is, you know, truly it is not shade. I don't know, you know, there is no any, for sure this is the shade. But yes, you are right. And based on my experience for all the facials that I worked, if you have very thick and very good, you know, with a high thickness of the lithology, it is very easy to understand for the model. For the rest of them, yeah, sometimes it is misleading for data, for the models.
Yeah, I see that usually gamma ray is used for a shale non-shale indicator, right? And only that one thin layer that you could predict, you can see a small spike in the gamma ray, but probably if you had, like you said, if you had used more columns, other logs,
yeah,
could be helpful, right?
We could use other logs, like we have PEF, we have other kind of lithology indicators, but again, just mechanics. I was looking for to not make it very, you know, computationally heavy or run a long time. I was looking for the codes, how neural networks without TensorFlow and actually PyTorch, we can do actually my neural network, and it's amazing for me actually.
Okay. And did you do any kind of research in this using your model to understand what was the most important of the features?
What kind of features we are going to use as predictor, you mean?
Yeah, the one that it's been most important, because for me, just by looking, I would say that it would be the gamma ray that is giving the best indicator, but it's hard to say just doing that. Probably you have to do some cross-validation and try to remove and include all those features and see which one is contributing more. Did you do something like that?
Actually, no. For this job, I didn't do, but based on my experience on petrophysics, yes, similarly, gamma ray is the best indicator for the lithology, especially for the sands and for the shales. But in some cases, for the carbonates, I'm sure nitron and density is very good indicators.
Okay. Oh, thank you.
So Ryan, very nice job. It's really very helpful to do all these things from the scratch. I was wondering, did you compare with the, for example, with the TensorFlow runs? Did you compare the two?
No, for this job, I didn't run it. And actually, I wanted to do that yesterday, I thought. But TensorFlow, I did very simple model. It did much better than this one, accuracy. And also, I can remember it could predict this thin layer here. You see that? But TensorFlow. But maybe for this work to improve it, we can add more wells, maybe, because this is just 7,000 points. for the data points, it's about 7,000. For the calculation cost, I didn't add it to, for example, 1 million, because the original data is about 1 million rows of data with 26 columns, and makes it huge matrix for this kind of work. But absolutely, TensorFlow should do much better than, because you have a lot of hyperparameters in TensorFlow. Like I said, we can use L2 to provide, to keep away from overfitting, or maybe I have another presentation for the Geo convention. I will talk about how we can optimize the hyperparameters for the facial recognition from the TensorFlow. It's gonna be how many layers, how many nodes, which activation. It is better to use. It is sometimes a costly function. It takes time, but it is good to have, how many layers you are. I made it layer here just by chance, okay? 20, 10, 8, but to optimize to how many layers, how many nodes, which activation I should use. I have some research on it, maybe, yeah.
Yeah, I was wondering, when you do things with TensorFlow, they have ways to optimize with graphs, right? Yeah. And in your case, you wouldn't. I don't think you did that. Like, it would be a lot of work. Of course, it wouldn't be worth to do. But I was wondering how significant will be the running cost difference, right? Between TensorFlow, that it will implement everything with graphs, that kind of just certain level of compilation, whether using pure Python, that it doesn't, right? So
absolutely. TensorFlow is very specialized, and I'm sure for the number of iteration that goes up, based on my experience, in number of iterations goes up, TensorFlow is doing better than this kind of, running your parameter by yourself. On the other hand, I'm not very in detail sure that TensorFlow using list or tuples, because I checked that tuples not much, about double times faster than the list computationally, not maybe two-thirds times, not double. And for the iteration, as long as we avoid for loops, the speed goes up. For loops destroy our calculation speed, and that's why here Andrew also didn't use for loops a lot in his codes. He tried to use vectorization in a Numpy. I'm not very familiar with vectorization, but I know that it goes like doing for loop job without doing for loop. It goes directly and much more faster in Numpy.
Right. Yeah. Yeah. Certainly, you have to like the way you do it. You did it is. I think it's the best you can do if you're only using Python, right? Like the graphs implementation with graphs is a lot more complex. So, for example, if you're using something, let's say like TensorFlow, Keras, if you customize anything with a function in Python, you will typically wrap that around a TensorFlow function. That what it does, it will convert it into it will do some sort of compilation. And in this case, basically you're customizing everything, right?
Yeah,
everything from beginning to end. So yeah, that's what I was curious how much. So do you find that that's the way you prefer to keep doing it with your own codes, or you did this mostly to learn, and then you say, well, I go back to the library?
Actually, it was for learning process for me. Actually, I wanted to, the main pushing behind me was how to calculate derivation, partial derivatives, and what it means. I can remember 4 years ago when I learned about the backpropagation. Okay, backpropagation, this is how we can implement, the implementation is very important. How to write a code, understand, I want to these parameters keep and let it these parameters, this one is not important. Yeah, but I've seen that some other libraries already developed for the deep learning, actually. One of them getting famous rather than the PyTorch, I forgot it. But the point is that, if your functions and your library is faster than others, you have high probability of the success in the running. Otherwise, why we should do this? Let's use the TensorFlow or use the PyTorch. But personally, I prefer to write my function my own, to understand it, to touch it.
Right.
Okay. Do you have any other questions?
Yes, please.
Okay, Felix.
Yeah. Okay, Ryan, very nice presentation. I just have a question about how did you handle the class imbalance for the lithology prediction? Because when we use ensemble methods, they are pretty good managing the imbalance classes, but when we train neural networks, I think we have to do a specific job in the programming. So I would like to know how can we do to solve this problem. Thank you.
Yeah, that's a very good question, Felix. For this project, I didn't check. I didn't find it very difficult for the balancing. Balancing problems comes from when one of the classes maybe 95% and another one is the 5%. But here, actually, maybe the real data is also similar like this. We have not like this. We have maybe 70% of the wells has a shale and 30% sand and the rest of the lithologies. Yeah, there are a lot of techniques to add more, lithology artificially. You can use a smooth application, SOMT. You can use scikit-learn library to increase your possible samples. But here, no, I didn't check, and actually, frankly, I didn't want to use here.
Fair enough.
Okay, thank you, Roy.
No problem.
Okay, any other questions? Okay, if you don't have a question, so now I'm gonna share my screen just to finish our event today. So now I'm sharing. And now I just would like to thank you everybody for coming. Please don't forget to follow us and to keep in touch with us in the Meetup, YouTube, Twitter, and LinkedIn. And I'd like to announce also that we're going to be entering now for a summer break, and they're going to be returning with their learning labs in September. So thank everybody, and see you in the next event.